Welcome to Abstract Algebra. This course is prepared by Ginaline Orizal, a Bachelor of Secondary Education, major in Mathematics, and facilitated by Sir Ruben Gambulao Jr. This will guide you through the foundational concepts of abstract algebra, focusing on group theory and permutation. So first, let me show you our objectives. So by the end of this lesson, the students will define key terms such as orbit, cycle, and permutation. They will integrate these concepts into group theory and learn to write permutations in cycle notation, performing related calculations. So let's start. Let us first discuss what is an orbit. So orbits, a permutation of a set, defines an equivalence relation. The equivalence classes formed by this relation are known as the orbits of permutation. Understanding orbits is crucial for grasping the structure of permutations. According to the proof of orbits, we verify the properties of reflexivity, symmetry, and transitivity. Reflexivity ensures each element relates to itself. Symmetry and transitivity confirm the equivalence relation, establishing the foundation for defining orbits. So we have here the example of orbits. Consider a permutation. By applying it repeatedly, we identify the orbit containing a specific element. This process reveals the structure of permutation, showing how elements cycle through their positions. Okay, next, cycles. A permutation can be decomposed into cycles, each acting on a distinct orbit. The decomposition helps simplify the analysis of permutations, allowing us to focus on individual cycles and their interactions. So we have here the definitions. A cycle in a permutation has at most one orbit with multiple elements. The length of a cycle is the number of elements it contains. This notation helps in representing and analyzing permutations efficiently. So examples of cycles. Not all permutations are cycles. By examining the orbits, we determine whether a permutation is a cycle. This understanding aids in identifying the structure and behavior of permutations. So we have again a theorem on cycles. Every permutation of a finite set can be expressed as a product of disjoint cycles. This theorem is fundamental in understanding the composition and decomposition of permutations. Example of cycle notation is by analyzing a permutation, we can express it in cycle notation. This representation simplifies the understanding of the permutation's structure and the relationship between its elements. In cycle decomposition, we explore how a permutation can be decomposed into cycles. This process highlights the distinct orbits and the interactions between elements within the permutation. So we have here a few remarks on cycles. The multiplication of disjoint cycles is commutative. The representation of a permutation as a product of cycle is unique, emphasizing the structured nature of permutation. Before we dive into the alternating groups, let us first discuss what is transposition. A cycle of length 2 is a transposition. Any permutation of a finite set can be expressed as a product of transpositions, providing a foundational tool for analyzing permutations. Examples of transpositions. We demonstrate how cycle can be expressed as products of transpositions. This flexibility in representation is key to understanding the underlying structure of permutations. So we have here, speaking of even and odd permutations. So a permutation is even or odd based on the number of transpositions it contains. This clarification is crucial for understanding the properties and behavior of permutations. So we have here the proof of even and odd permutations. We explore the relationship between permutations and transpositions. By examining the orbits, we determine the parity of a permutation, enhancing our understanding of its structure. So according to its definition, the even and odd permutations, a permutation's parity is determined by its expression as a product of transpositions. This concept is essential for analyzing the symmetry and the properties of permutations. Since we already discussed what is transposition, even and odd permutations, let us now dive into the alternating groups. So the set of all even permutations forms a subgroup known as the alternating group. This subgroup has significant implications in the study of symmetry and group theory. So the proof for alternating groups, we demonstrate that the alternating group has half the elements of the symmetric group. This proof highlights the balance between even and odd permutations within the group. So the definition for alternating groups we have here, the alternating group consists of even permutations. Understanding this subgroup is vital for exploring the deeper properties of symmetric groups and their applications. In exploring the structure and behavior of permutations through orbits, cycles, and the alternating group, this report highlights the fundamental role these concepts play in understanding the symmetry and organization within group theory. Orbits and cycles provide insight into how elements are mapped and rearranged under permutation actions, while the alternating group exemplifies a significant subgroup characterized by even permutations. Together, these ideas deepen our comprehension of group structure and lay the groundwork for more advanced algebraic study, including Galois theory and applications in geometry and number theory. This discussion reinforces the interconnectedness of these concepts and their essential place in the broader framework of abstract algebra.